Have you ever looked at a tangent graph and just thought, what in the world is going on here? Well, you are definitely not alone. It looks nothing like its cousins, sine and cosine. So today, we're going to crack this thing open and figure out exactly what makes it tick.
You know, we're all used to the smooth, predictable waves of sine and cosine, right? They flow so nicely, but then tangent comes along and it's all broken up into these weird, separate pieces. What's up with that?
So, that's the big question we're going to solve together. Why does the tangent graph look so completely different from the other two?
And here's the best part. The key to this whole mystery, it's not some super complicated thing. In fact, the entire story is hidden right inside its most basic formula.
And there it is. Tangent of theta is just sine of theta divided by cosine of theta. That's it. This one simple fraction is the reason for all of the graph's seemingly bizarre behavior.
Now, I want you to think all the way back to basic math class. What's the number one unbreakable rule when you're dealing with fractions? What happens when that bottom part, the denominator, in this case cosine theta, hits 0?
Exactly. You can't do it. Division by 0 is undefined. So for every single angle where cosine equals 0, the tangent function just doesn't exist. And on the graph, these spots create these forbidden zones, these vertical lines we call asymptotes. The curve will get infinitely close to them, but it can never ever touch or cross them.
So we can pretty much boil down the entire structure of the tangent graph to just two simple rules. Think of it like a playbook. Rule 1. When the top of the fraction, sine, is 0, the whole thing is 0. Bam! That's where the graph crosses the horizontal axis. Rule 2. When the bottom of the fraction, cosine, is 0, you get an error. It's undefined. That's where we draw our vertical asymptotes. That's the whole game. And those two rules are what create all of these key features you see right here. Now look closely. Notice the period, how long it takes for one full cycle to complete, is pi. Just pi. That's half the period of sine and cosine, which is a huge deal. The asymptotes and zeros follow a really predictable pattern, and that little n in the formulas just means you can plug in any integer, like 1, 2, 3, or -1, -2, to find the next one in the sequence. This also means that even though there are these gaps where x can't exist, the y values go all the way from -infinity to +infinity.
Okay, theory is great, but let's actually get our hands dirty and see how these rules work in the real world with a couple of typical problems.
All right, here's a classic example you're almost guaranteed to see. We need to find all the vertical asymptotes for the tangent graph, but only within this specific window, from -2 pi to +2 pi. And it's a really straightforward process. First, we just grab our general formula for the asymptotes. Step 2, we start plugging in integers for n, like -2, -1, 0, 1, and we just see which of those answers actually land inside our required interval. And that gives us our final answer right there. Super simple once you know the rule.
Okay, let's level up just a little bit. What happens when we stick a number inside the function, right next to the x, like in y equals tangent of 2x? Well, that's going to mess with the graph's period.
So the key here is to identify that b value, which is just the number multiplying x. In our case, it's 2. Then we use the period formula for tangent, which is pi divided by the absolute value of b. So we get pi over 2. This basically means the graph is horizontally squished. It now completes a full cycle twice as fast as the original graph.
Now hold on, before we go any further, I want to call out the single biggest mistake people make with the tangent graph. Seriously, if you remember only one thing from this whole explainer, please make it this.
The natural period of a basic, unaltered tangent function is pi, not 2 pi, pi. It repeats itself every 180 degrees, not 360 like sine and cosine. This one little fact is the source of countless wrong answers.
So please, I'm begging you, burn this into your memory. We spend so much time with sine and cosine that our brains are hardwired to use 2 pi for everything. With tangent, that is a trap. It is always, always, always wrong. The correct formula is pi divided by b.
So you might be thinking, okay, this is a neat function that flies off to infinity, but why should I care? Does this abstract math ever actually show up anywhere? And the answer is absolutely.
In fact, if you've ever driven a car up or down a steep hill, you have experienced a real-world tangent function, probably without even realizing it.
See, civil engineers use this term called road grade to measure how steep a road is. When you see a sign that says 6% grade, it just means for every 100 feet you drive forward, the elevation changes by 6 feet. And the formula for that percentage? It's literally just the tangent of the road's angle multiplied by 100.
And this is where it all comes full circle. Think about it. As a road's angle gets steeper and steeper, as it gets closer and closer to a vertical 90 degrees, what happens to its tangent? It shoots toward infinity. That asymptote on the graph isn't just some abstract line anymore. It's the mathematical equivalent of driving straight into a vertical cliff face.
So you see, the tangent graph isn't just some weird curve in a math book. It's a perfect model for any system that has a critical limit, a tipping point where getting too close causes some value to just explode. It kind of makes you wonder, doesn't it? What other systems out there, in engineering, in economics, maybe even in biology, behave in exactly the same way?